part 4, we ask and answer the question, what can we do toward phosphorus sustainability? And the first thing we'll define is what we mean by sustainable. To have a sustainable management of the phosphorus cycle, we say that we need to address the needs of the present, such as food security and water quality, without compromising the needs of the future, for example, through negative impacts on the environment. This is not simple, of course, given what we've already learned about phosphorus in this module. Nevertheless, it's a vision that guides actions we can take as individuals and as citizens, as educators, and as researchers. And in designing and executing actions towards sustainable phosphorus management, we consider what is called the triple bottom line factors to sustainability, which includes the environmental and health factors, the social and ethical factors, and the economic factors. Inspired by this picture of a meal, something we can all connect to individually, let's first look at how individual decisions such as diet can affect phosphorus flows. On this slide, we'll populate a diagram showing phosphorus flows through the food that we consume. Then on later slides, look at the quantities of phosphorus sources and flows for different types of representative foods. And before we start, I'll add that this is a qualitative, not a quantitative diagram. It's also imperfect because of nuances all along the flow. Nevertheless, it's a useful educational tool to illustrate several important factors. We start with phosphorus in the human diet, which mostly comes from packaged foods, and then the flow of output phosphorus to wastewater treatment plants. This food is made from crops, which used fertilizers, which were sourced from mined phosphate deposits. But a considerable part of the population eats meat products. So we add the use of crops to feed animals, which then also ends up in the human diet. We've also been introduced to phosphorus runoff from agriculture and humans, shown here. And finally, we should note that there's both recycling of phosphorus and placement of phosphorus in landfills in various steps of this process. Now, we've populated a relatively complicated schematic, but one important takeaway is that mined phosphorus is likely used to grow the food that you eat, whether it's plant-based or animal-based, and that upstream inefficiencies affect how much mined phosphorus is required to grow the food. Moreover, the phosphorus that we intake has to go somewhere, for example, to landfills, to rivers. Now, on the next slide, let's look at how much phosphorus is in some representative foods that humans consume. The United States Department of Agriculture, or USDA, reports the average phosphorus content in various types and amounts of food. The table at the right includes just a few that were extracted from the USDA database. A serving of beef, for example, may contain 263 milligrams of elemental phosphorus. That sounds pretty good if you remember that the recommended daily allowance for phosphorus in adults is 700 milligrams. An egg, by comparison, contains on average 99 milligrams of phosphorus, and a cup of apples, 14 milligrams. Now, referencing that prior slide, which showed that mined phosphorus is used far upstream to produce these foods, we can ask the question, how much mined phosphorus is required to yield these foods? It's not an easy question to answer, in part because of limited data, and in part due to uncertainties and the heterogeneous nature of food production. Tomatoes grown via conventional farming will be different than tomatoes grown organically or through hydroponics, for example. However, if we allow ourselves to look at the averages based on some global data, we can show some useful examples. About a decade ago, Genevieve Metzen researched the amount of mined phosphorus required on a globally average basis to produce certain weights of food products. And some of her results are shown here. Note the highest bars for meats, followed by eggs, then fruits and vegetables are barely visible on the graph. Using the globally averaged values, we can calculate the amount of mined phosphorus required to produce these foods on the left, again, globally averaged. Starting with the egg in the middle, to produce a 60-gram egg requires on average 166 milligrams of mined phosphorus at the beginning of the food system. Compare this to the 113 grams of beef. We see that around 2,000 milligrams of phosphorus are required to yield it, a significantly more amount of phosphorus than that required to yield the egg. Finally, looking toward the apple. To produce 100 grams of apples on a global average basis, only 10 milligrams of mined phosphorus is required. At first, this seems unexpected to be able to generate 14 milligrams of phosphorus in an apple serving with only 10 milligrams of phosphorus input. But this reminds me of my childhood in Indiana, where we grew apples in our yard with zero application of mined phosphorus. And the example also illustrates the heterogeneity in how food is produced through different processes and in different regions of the world. Nevertheless, the example also illustrates the upstream phosphorus demands for our food. For those of you watching who may want to normalize these values to a constant mass, these values are shown at the right. The amount of mined phosphorus on a global average basis to yield 100 grams of the food product. From this research, Metzens showed that about 72% of the global average dietary phosphorus footprint between 1961 and 2007 was due to the consumption of animal-based food groups. Now, to be clear, this exercise enables us to see more of how the food we eat influences phosphorus demands upstream at the beginning of the food system. This information can be combined with your own personal dietary needs and preferences in establishing your own healthy diet, while being more aware of how we each individually exist in the larger system. At the other end of the human consumption is human waste, and there is heterogeneity in how we deal with human waste. While most of us are familiar with wastewater treatment plants, there's a large part of the world that is disconnected from these plants. In some cases, they use off-grid systems like septic systems. There are also innovations in capturing human waste, for example, using urine diversion toilets, such as the one shown here. And in France this past summer, I took a photograph of this public urinal, which can be used to capture urine at the source before it gets diluted downstream in the treatment system. To reinforce the complexities associated with phosphorus flows, and in reference to personal dietary choices, it's useful to note that moving to entirely plant-based diets, although decreasing demand for mined phosphorus, would also increase losses to waterways from human waste. This balance between reducing phosphorus input needs versus reducing phosphorus waste is not something that can be solved overnight, and it points to the complexity of the phosphorus sustainability problems. There are macro scale and systems level models out there that allow us to see how various interventions can help to address some of these challenges. This particular data expresses the relative environmental impacts. Using 2010 as a reference, if we do nothing, then by 2050, there will be a 50% increase in the environmental pressures. There are various things we can do which can impact pressures to various extents. Dietary changes can help, but population growth overwhelms the potential impact of dietary changes. We can also reduce food loss and waste, but it's still not enough to pull back to baseline levels. The single factor that can help the most was identified as improving technologies and management of phosphorus. And here we need innovation. Moreover, if we combine these factors, and we call this the convergence of solutions at the right, the models show that we can potentially bring back environmental pressures to below 2010 levels. And while this data shows us the environmental pressures downstream, we can also look at how possible interventions and innovations can address our phosphorus demands upstream. In section 2, we looked at how the annual amount of mined phosphorus increased over time. If we project that data to the future and do business as usual, we see that the requirements continue to increase with population growth. However, there are various demand measures and supply measures that can be used to enhance phosphorus sustainability. For example, efficiency in agriculture and food systems, changing some diets and reusing food, human and animal waste. If we can be successful at advancing all of these areas, we could significantly affect phosphorus demands and advance phosphorus sustainability. To close part 4, I'll emphasize that to advance phosphorus sustainability, we need many things. We do need to better understand individuals' dietary choices, but we also need innovations in phosphorus management technologies and best practices, for which research development is needed.